We're going to look at a couple different ways of analyzing data to determine whether a linear or quadratic model is appropriate. So the first method that we'll look at will be using finite differences. And what's important to know here is that a linear function will have constant first differences, while a quadratic function will have constant second differences. And we'll look at what first differences and second differences are in a moment. So let's look at an example with a table of data. Here we've got xy values of 10, 0, 11, 1, 12, 2, 13, 3, 14, 4. And with this method, what's important first to check is that the x values are going up by a constant value. So from 10 to 11, we're going up 1. From 11 to 12, we're going up 1. From 12 to 13, we're going up 1. From 13 to 14, we're going up 1. So our x values are going up by a constant value. Now let's look at how our y values are changing. From 0 to 1, we'll look at 1 minus 0, and our difference is 1. From 1 to 2, we'll look at 2 minus 1, and our difference is 1. From 2 to 3, we'll look at 3 minus 2, and our difference is 1. From 3 to 4, we'll look at 4 minus 3, and our difference is 1. These are the first differences. And here we see that we have a constant first difference, and that constant first difference equals 1. So because we have a constant first difference, this is a linear function. The 3 dots in a triangle mean therefore, so that statement reads, therefore, this is a linear function. If we were going on and writing the equation of this linear function, that constant first difference of 1 would actually be the slope. Let's look at a second example with another table of data. Here we have 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. Again, let's check that our x values are going up by a constant value. So from 0 to 1, going up 1. 1 to 2, we're going up 1. From 2 to 3, we're going up 1. From 3 to 4, we're going up 1. Now let's look at our first differences. From 0 to 1, we'll look at 1 minus 0, and our difference is 1. From 1 to 4, we'll look at 4 minus 1, and our difference is 3. From 4 to 9, we'll look at 9 minus 4, and our difference is 5. From 9 to 16, we'll look at 16 minus 9, and our difference is 7. So here, our first differences are not constant. So because our first differences are not constant, that means we do not have a linear function. But we're going to repeat this process on these first differences and look at our second differences. So from 1 to 3, we'll look at 3 minus 1, and our difference is 2. From 3 to 5, we'll look at 5 minus 3, and our difference is 2. From 5 to 7, we'll look at 7 minus 5, and our difference is 2. So these 2's are our second differences, and here they're constant. So here, our second difference equals 2. And because we have a constant second difference, that means this is a quadratic function. Let's look at a third example. So here we have the xy values 1, 12, 2, 6, 3, 4, and 4, 3. So again, let's check that our x values increase by a constant value. So 1 to 2 goes up by 1. From 2 to 3 goes up by 1. 3 to 4 goes up by 1. So it's increasing it by a constant value each time. Let's look at our first differences. From 12 to 6, we'll look at 6 minus 12, and our difference is negative 6. From 6 to 4, we'll look at 4 minus 6, and our difference is negative 2. From 4 to 3, we'll look at 3 minus 4, and our difference is negative 1. So here, we do not have constant first differences. So that means this is not linear. Let's look at our second differences. So from negative 6 to negative 2, we'll look at negative 2 minus negative 6, which equals 4. From negative 2 to negative 1, we have negative 1 minus negative 2, and our difference is 1. And here we see that our second differences are not constant. So that means that this is not quadratic. So because right now we're only looking at linear and quadratic and it's neither of those, we would say that this is neither. In the future, we'll learn to distinguish another possible relationship as well. So that was the first method, using finite differences. The second method is to look at a graph of the data, and that can give us a feel for whether it's linear or quadratic or neither. But this method is not as exact as looking at finite differences. So that first table of values we looked at, where we had constant first differences, we had the values 10, 0, 11, 1, 12, 2, 13, 3, 14, 4. And if we plot these, we're going to use a scale of 2 on the x-axis and a scale of 1 on the y-axis in order to fit this data in. And 10, 0, we've got 11, 1, we've got 12, 2, we've got 13, 3, and 14, 4. And these points appear to fall along a line. So I can draw a line through this. And if you recall, we had constant first differences, and this does look like it's a linear function. Let's look at our second table of data. This is the one that had constant second differences and ended up being quadratic. Here we have 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. So let's plot these points. So 0, 0, 1, 1, 2, 4, 3, 9, and 416 is about here. And if we connect these, this does appear to be part of a parabola. So this does confirm what we found with finite differences, that this is a quadratic function. But without having checked that the second differences are the same or constant, we could not be sure from this graph alone. Let's look at our third graph, our third table of data. We had 112, 26, 34, 43. And if we plot these points, I've got 112, 26, 34, 43. And if I connect these, we can't be sure because this doesn't look much different from the graph above, which was quadratic. But if you recall, when we looked at finite differences, this was neither linear nor quadratic. And so this is neither, but you can see here that by graphing, this is not always clear, and that we would need to really conduct an analysis using the finite differences, or we'll learn about another method in another video using regression.